Section 6.2, linear and angular velocity. We've got three main topics here to talk about in section 6.2, and let's just get started. The first one is angular displacement. Now, you've talked about displacement before probably in physical science, probably in physics if you've taken it or are currently taking it. Displacement is just it's a change, and when we're talking angular displacement, it's simply the angle of rotation. How far does something rotate? So in this example, these couple of examples here, we're just looking at how far something has rotated, what angle it has turned at. So if I went one revolution, my angular displacement, my angle of rotation would be 360 degrees. Or if we're talking in radians, that would be 2 pi radians. Or we could turn it into just a number without pi and take 2 times pi, which would be 6.28 something radians from there. Okay, so in these examples, first couple, determine the angular displacement in radians, round to the nearest tenth. So 4.5 revolutions, what we're going to do is we're going to take 4.5 and we're going to take it times 2 pi, because there are 2 pi radians in one revolution, 360 degrees, 2 pi radians. So 4.5 times 2 pi, well, that would be 9 pi, and you can type in 9 pi in your calculator and you would get something along the lines of 28.3 radians. And that would be your answer there, 28.3 radians. It rotated a total amount of 28.3 radians in 4.5 revolutions. For number 2, 8.7 revolutions, we're going to do the exact same thing. We're going to do 8.7 times 2 pi. If you want to do 8.7 times 2, you can. If you want to just type in 8.7 times 2 pi in your calculator, you can do that too. 8.7 times 2 is 17.4. And 17.4 times pi gets you approximately 54.7 radians. Okay, so there's the basic first idea, angular displacement. How far, how many degrees, and it wouldn't be degrees, what's the angle of rotation in a certain number of revolutions? Leading up to that, or building on that, is the idea of angular velocity, and that's the next vocabulary term, angular velocity. It's a ratio of change in the central angle to the change in time. Usually we're talking seconds, could be hours, could be days, could be minutes, could be weeks. Usually it's going to be seconds. So the ratio and change in the central angle to the change in time. So how we're going to do this, and I'm going to show you the symbol for angular velocity in just a second. But how you find it, it's equal to your degree over your unit of time. Now the degree, this is your angular displacement. Angular displacement. How many degrees, or what was your angle of rotation? Displacement. T, generally T stands for time, and this is no different. The symbol for angular velocity, it's the Greek letter omega, specifically the lowercase omega. And it kind of looks like this. It kind of looks like a curly W. Let me try to draw that again. Kind of a curly W. That's kind of that's the gist of it. This is the Greek letter omega. If you want to just make a W, I'm okay with that. We'll know that stands for angular velocity. But angular velocity is the angular displacement divided by the amount of time it took. So let's try a couple of examples here. 5.8 revolutions in 9 seconds. Now we need to know the angular displacement first, and we don't know that because we just have the number of revolutions. So what we need to do first is we need to find our angular displacement, but we can also put in our time at the same time. So we can say our angular velocity is equal to our angular displacement, which is 5.8 times 2 pi, because that's one revolution is 2 pi radians, divided by 9 seconds. Okay, angular displacement, take the number of revolutions times the number of radians in one revolution, which is 2 pi, divided by our unit of time. And when you type all that in your calculator, what you're going to get is approximately 4.0, or just 4 radians per second. Okay? Number 2, 7.3 revolutions in 5 seconds. We're going to do the same thing. So Greek letter omega is equal to 7.3 revolutions times 2 pi radians in one revolution, divided by the amount of time it took to do those 7.3 revolutions. That'd be 5 seconds. And we're going to get approximately 9.2 radians per second. That one's rotating pretty quickly. If we're covering 7.5 almost, or 7.25 revolutions in 5 seconds. We're twirling around pretty quickly. The third idea is the idea of linear velocity. And linear velocity, that's just a distance traveled per unit of time. That's something that you've learned about in physics, in physical science, maybe even some earth science. We're just kind of touching on it again here in pre-calc. So linear velocity is just a distance traveled per unit of time. Now, specifically, we're thinking about linear velocity on a circle. So how fast we're moving. So if we have a circle, how fast are we moving from here to here, depending on how long it took and what the radius of that circle is. That's what we're going to be able to find with linear velocity on a circle. The formula for linear velocity in a circle: velocity is lowercase v is equal to the radius times the angular velocity. So that would be theta over time. Okay, if you want to shorthand it, it's v is equal to r times omega. And if you want to put that in parentheses, you can, but you don't necessarily have to. Okay, it's the radius times the angular displacement, or not the angular displacement, the angular velocity. Radius times angular velocity. That's how you find linear velocity on a circle. So, determine the linear velocity of a point rotating at an angular velocity of 17 pi radians per second. I don't have a pi button on my keyboard when I type this out, so I just wrote pi. So we're rotating at 17 pi radians per second at a distance of 5 centimeters from the center of the rotating object. So that is our radius here. That's going to be important. So is 17 pi radians per second. And we're supposed to find the linear velocity of that point on that circle rounded to the nearest tenth. So velocity is equal to our radius times our angular displacement over time. So let's fill this in. Our velocity is equal to, our radius is 5. Our rotations is 17 pi radians per second. So this is our angular displacement, 17 pi radians per second. So we're going to have 17 pi radians per 1 second. Now, if it's over 1, we don't really need to put over 1, but that's not always a bad thing, just to make sure we have everything filled in. And then we just need to take 17 pi times 5, and what we're going to get in the calculator is approximately 267.0, or 267 centimeters per second. So we're moving pretty quickly around that circle when we're rotating at 17 pi radians per second. Let's try another one here. A carousel rotates at 0.275 radians per second. A rider on the inside row of horses is 11 feet from the center, and a rider on the outside row of the horses is 20 feet from the center. The question here is, how much faster is the outer rider traveling than the inside rider? So what I think we need to do is we need to figure out the linear velocity of both riders, and then we'll just find the difference, because that's really what it's asking for, is how much faster, or what's the difference between the two velocities. Let's start with the inner. So the inner velocity, our radius is, no, that's not our radius. Our radius on the inner is 11 feet. Okay, so our radius is 11. Our angular displacement, our angular velocity is 0.275 radians per second. So 0.275 over 1, which is really just going to be 0.275. So our velocity then for the inner rider, v, is equal to our radius times our angular velocity, which is going to be just 0.275. And when we do that in our calculator, we're going to find that our linear velocity of the inside rider is 3.025. Let's see, that's going to be feet per second. Ft over SEC. Now that is an exact answer, because we know, or based on, we're assuming that this is an exact number, and 11 feet is also an exact number. And if it's just 3 decimal places, I think we can go ahead and write that out. For the outside rider, for the outer rider, we're going to do the same thing. Our radius for the outside rider is, let's see, it's 20 feet. So the radius is 20. Our angular velocity is going to be exactly the same thing, 0.275. To find the linear velocity, do the same thing that we just did for the inner. Take the velocity is equal to our radius, which is 20, times our angular velocity, 0.275. And when you type that one in your calculator, you're going to get 5.5 feet per second. But the question's asking, how much faster is the outer rider traveling than the inside rider? We need to take these two velocities and subtract them. We need to go 5.5 minus 3.025. And when we do that, we get 2.475 feet per second faster. So the outside rider is traveling at almost 3 feet per second faster than somebody on the inside. So the total amount of distance covered, if we knew how long we were going for, how long the ride was, let's say it was 10 seconds, then we'd be going 24 feet further if we were on the outside than the inside. If it was a 100 feet or 100 seconds longer or a 100-second ride, the outside rider would go 247 feet farther than the inside rider. Last example here is a little bit more challenging. The tires on a race car have a diameter of 30 inches. If the tires are rotating at a rate of 2,000 revolutions per minute, determine the car's speed in miles per hour. We have several things we need to do here. I'm going to start by just rewriting the formula for linear velocity, because that's really what we're looking for. Linear velocity is equal to the radius of our object times the angular velocity that we were rotating at. Angular, I'm just going to abbreviate velo, angular velocity. Okay, we have two things we need to figure out. We need to figure out the radius, because it doesn't tell us the radius, it does tell us the diameter, and we need to figure out the angular velocity. It tells us some of that, but the problem is it's given us inches, and we need to know miles, and it's giving us minutes, and we need to convert that to hours. So let's kind of break this down piece by piece. The radius here. So the radius, we know that the diameter is 30 inches, so then the radius is going to be 15 inches. And what we're going to need to do, and I'm going to rewrite that, I-N-C-H-E-S. What we need to do is we need to convert this to miles, because our unit is not correct. We need miles, and we have inches. So I'm just going to make a little note here. Convert to miles. And what we're going to do here is a process called dimensional analysis. You probably have done this in physical science or chemistry before. Maybe not have heard that specific phrase, but basically we're going to convert one unit into another. Okay, so how we're going to do this, we're going to have 15 inches, and how we're going to convert this, I'm just going to make this a fraction. I'm not going to worry about the numbers right now. What I'm going to do is I'm going to focus on the label. Okay, in this case, inches. If I have inches in the top and I need to cancel it using a fraction, my next inches needs to be on the bottom. Okay, so I'm going to put inches there. The next unit of measurement that I think we should use is probably feet, because I know that there are 12 inches in 1 foot. So if I have inches on the top and inches on the bottom, those units cancel out. So my new unit here is feet, but I'm still not there because I need miles. So I need to keep going. If I have feet on the top, I know my next unit for feet has to be on the bottom, and then from feet I do know how many feet are in a mile. So I can say 1 foot, 1 mile is equal to 5,280 feet. So I have feet on the top, I have feet on the bottom. Those units or those labels cancel each other out. So now I don't have label, no. The only label I have left is miles. Okay, so if I want to, write this all out, I could. Otherwise, I can just kind of leave it like this, because we're going to type this all in our calculator here in just 1 second. So to convert 15 inches to the number of miles, we take 15 times 1 times 1 and divide it by 1 times 12 times 5,280. And that'll be the number of miles in 15 inches. It's not going to be very big. It's very small, actually. Let's do the same thing for our angular velocity. So our angular velocity is right now at 2,000 revolutions per minute. If we go back to angular velocity, let me go back here. Angular velocity is always in radians per second. And right now we don't have that. We have revolutions per minute. Okay, so let's turn this into something that we can work with. We need to convert to radians over, and in this case we don't want minutes, we want hours. Okay, so we might have 2 labels to cancel here or to convert. Let's give it a shot. So we know that we have 2,000 revolutions in 1 minute. The problem sets it up and tells us that. Okay, we need to choose one of these 2 labels to cancel out. It doesn't matter which one. I'm going to choose revolutions just to get rid of that one first. So revolutions, and we can turn that into Radians, that's a really bad radians. Let me try writing that again. R-A-D-I-A-N, okay? In 1 revolution, how many radians are covered? That would be 2 pi. There are 2 pi radians in 1 revolution. So if I'm looking at the labels, this revolution, 1 on top, 1 on bottom, they will cancel each other out. So now my units here is radian per minute. Excuse that bell, it's the middle of the school day here. So right now our unit is radians per minute, but we need radians per hour. So radian's going to stay. We're done with this one. We need to convert minutes now. So if I have minutes on the bottom, the next minute I need to put is going to be on the top. And I'm looking for hours as my unit of time. So I know how many minutes are in an hour. I can say that 60 minutes make up 1 hour. So if I have minutes on the bottom and minutes on the top, those units cancel out. So my new unit here, radians on top, hours on bottom, that's exactly what I want. Okay? If you want to try simplifying things, actually nothing here is going to simplify. So we can just go about actually finding our linear velocity now. We know our radius in miles. We know our angular velocity, in this case radians per hour. Our unit of time that it wants is hours. So we converted minutes to hours. We converted revolutions to radians. Let's put it all together. I'm going to rewrite this here in green. Our velocity is equal to our radius times our angular velocity, degree or angle per unit of time. So let's fill in what we know. We know the radius was going to be, and I'm just going to rewrite those 3 fractions without the labels. We don't necessarily need those. It's going to be 15 over 1 times, it was 1 over 12 times 1 over 5,280. And this is going to be times our angular velocity. And I'm just going to rewrite these 3 fractions again without the labels. But this pi is not a label. It is a number. It needs to stay. So it's going to be 2,000 over 1 times 2 pi over 1 times 60 over 1. That is going to be our linear velocity, how fast this race car is going in miles per hour. If you want to just type this all in your calculator, you can. It really doesn't matter which way you want to do it. It's all multiplication, so you can put parentheses around everything if you want. You could go 15 over 1 times 1 over 12 times 1 over 5,280 times 2,000 times 2 pi times 60. That would be perfectly acceptable to put in your calculator, and that's fine if you want to do that. If you want to try to clean up the numerators, just take 15 times 2,000 times 2 pi times 60, and then do the same thing with the denominators and go from there. It's up to you, really, however you feel most comfortable. In the end, what you're going to find out is that this race car at 2,000 revolutions per minute with a 30-inch diameter tire this race car is going 178.5 miles an hour, which is pretty accurate. Most race cars, think about the races on Sundays, the big races, the national races, they're going upwards of 200 miles an hour. This is probably not that unrealistic of an answer.